second. There we go. All right, ladies, gentlemen, good morning. Happy Wednesday morning. This is April 8th. It is Algebra 2 CP, period A1. Just a couple of reminders before we get started, the usual reminders. Make sure that your microphone is muted and your webcam is disabled for the duration. If you do have a question, though, please feel free to speak up and ask. Make sure that you also fill out that attendance form on Google Classroom as well, just to mark that you're here. It's the same form every day. Just go in and click that you are present for the day. All right. Today, what I would like to do with you is I would like to go through some review problems in preparation for the summative assessment. We did have our progress assessment due as of 2 minutes ago at the start of class today. Hopefully everybody was able to get that done and everybody was able to send it via email. If you had any technical issues with that, like your attachments didn't work or you couldn't figure out how to attach a file or anything like that, please let me know in the chat and I'll be happy to address you at the end of class today and walk you through how to fix that. But again, hopefully that progress assessment is done. I want to give you one more reminder about the summative assessment as well. I did post a test review on Classroom. I did it just this morning, so hopefully you can see that. Or actually, I think I scheduled it to pop up on Classroom at the end of this class. So if you haven't seen it, you will see it very, very soon. It should pop up on your Classroom feed at 10:30. So that is a comprehensive summative assessment review on everything that your summative assessment entails. That summative is going to be on April 14th, so keep that in mind. As we discussed in previous classes, it is going to be an email that I send out at about 8 o'clock in the morning, and I've decided that I'm going to give you until 6 o'clock p.m. that day, that's a 10-hour block, in order to take a picture of it, complete your work, take a picture of it, and send it back to me, okay? I think that's more than reasonable. The reason I accounted for so much time is just because there's a lot of unpredictabilities when working in a home setting that I want to make sure I account for. Okay, so that's why you have that amount of time. It doesn't mean it's a 10-hour assessment. It means it's a length of a normal summative assessment. Just, you have a lot of time to get it done. That's a big window of time, so you can plan accordingly. Another thing I want to mention about the summative is that we, and by we I mean the Algebra 2 CP teachers, have decided that for CP we are not going to be featuring word problems on the summative. So the summative is only going to feature your solving equations and your graphing. Okay? The reason why we decided to exclude word problems is because with the distance learning disruptions, some people had to rush word problems, and I don't think everybody I don't think it's fair, given the current circumstances, to ask word problems on a summative assessment, especially, in the midst of distance learning and everybody acclimating to it and whatnot. I know from class to class, the transition was smooth for some people and not smooth for other people. So regardless, long story short, is that you do not have to worry about word problems on the summative, but there will be solving equations and there will be graphing. Probably about 4 of each. I think there's 8 total problems. I'll make sure I double check on that. That could be 10, but it's somewhere in that vicinity of that amount of problems. Okay? So again, that's going to be coming your way on April 14th. You're going to have that 10-hour window to complete your work, take a picture of your work, and submit it to me. By the way, if you're wondering, that is a day that our class is scheduled to meet. During that half-hour session of our class meeting time on April 14th, and I will send this information to you via email just as a reminder, I am going to ask that you stop in just to check in and say, hey, Miss Giorgio, I'm here. I'm not skipping out on you today. And it will be that time for you to ask any questions that you have. So it's not going to be a lesson that I record and upload like I've been doing with all my traditional ones. It's going to be just me sitting here. If you have any clarifying questions, you can feel free to ask. I can't at that time walk you through how to do a problem. That's not fair. But if you have any clarifying questions about the summative, I can definitely be here to address those. Okay? All right. So hopefully that gets all the information out that you need. Again, I will send all that information via email, so make sure you check your email as just a nice reminder. But I guess that's one other thing I wanted to tell you too, is make sure that you are checking your email regularly, because it's important that you keep up to date with the information that teachers, myself included, are sending you. All right, so without any further ado, let's go into a little bit of test review. Today, like I said, I'd like to review a couple problems on graphing and a couple problems on solving, because that is what is going to be on the summative assessment. So let's start with a couple graphing problems, 1 square root and 1 cube root, just to refresh your memory on how to do that. And then we'll go into solving problems, one with the single distribution and one with a double distribution, again, just as a nice refresher. So let's get started. Okay, let's start with our graphing review. starting out by graphing radical functions. And we'll start out with a nice square root function of f of x equals the opposite of the square root of 2x minus 5 and then plus 3. Okay? So if I'm faced with a problem like this, yes, what I would like to do first is I would like to go ahead and try to create a chart. Because if you remember, graphing radical functions is all about goals. It's all about being able to find nice, easy values for x that you can go ahead and plug in to your equation so that you get easy answers to work with, right? It doesn't make sense to plug in values for x randomly. It makes sense to do it strategically. So that's really what we're going to try to do, okay? Our first goal is I would like to plug in a value in for x that allows me to take the square root of 0. And the reason why it's the square root of 0 specifically is because that's the first perfect square. What value for x allows me to do that? So you're looking for what value, if I plug it in, will make this inner portion equal to 0. You might think to yourself, Mr. Giorgio, I don't know what's going to make that equal to 0. And that's fine because we have our nice backup strategy. You could say, well, if you can't see it off the top of your head, figure out what value for x will make that piece equal to 0. When is 2x minus 5 equal to 0? We can add 5 to both sides and divide by 2 and get that x is 5/2 or 2.5. Okay, 2.5. All right, so if you cannot see it off the top of your head which value to plug in for x, you can always make a little miniature equation like that. Okay, we know that if I take this value and plug it in, it's going to result in getting 0. That's why I picked it. The square root of 0 is still 0. The opposite of 0 is still 0. Plus 3 is 3. So our first point, our starting point, is at 2.5 or 5/2, comma 0. Okay. Does that make sense to everybody why that's the case, hopefully? Now we go forward from there and I say, well, what about the square root of 1? That's the next perfect square value, right? Makes a lot of sense if I want to plot a point. Let's figure out what's going to give us 1 because that's going to be an easy calculation. The value that gives us 1, again, you could make a little equation to figure that out, or you could look in your head and say that it's 3 because 2 times 3 would be 6 minus 5 would be 1. Okay? But again, if you can't see that, make an equation and say, well, when is 2x minus 5 equal to 3? Oh, sorry, not equal to 3, jeepers, equal to 1. You can add 5 to both sides. You get 2x is equal to 6, and divide by 2, you get x equal to 3. Okay? So that's how you know that you need the value of 3 in order for that middle piece to equal 1. Okay? Once you plug in 3, you know you're going to get 1 here. The square root of 1 is 1. The opposite is negative 1, plus 3 is positive 2. So your next point would be at 3, comma 2. After that, we're looking to plug in the square root of 4. What value is going to make that happen? I think I have to make an equation for this one. I can't see this one off the top of my head, so I just set up a little equation of when does 2x minus 5 equal 4. Add 5 to both sides, you get 2x equals 9, and divide by 2, you get x equals 9/2, which is 4.5. Okay? You know that when you take this value and plug it in, you're going to get 4. The square root of 4 is 2. The opposite is negative 2. Plus 3 is positive 1. And last but most certainly not least, we're looking for the square root of 9. This one I can see off the top of my head, but it's okay if you can't. You could always, again, make an equation. This one's going to be 7, though, because 2 times 7 is 14, and 14 minus 5 is going to equal 9. So when you do that, you get 9 under the radical. The square root of 9 is 3. The opposite is negative 3, plus 3 is 0. So now we have all our coordinates. You can keep going, of course. If you were to keep going, you would do the square root of 16, then the square root of 25, then the square root of 36, then the square root of 49. You're just always looking for those perfect squares because that's what's going to make your life easy and avoid decimals when you go to plug it in. Okay, like complicated decimals. You might get halves and quarters and things like that, but you don't want to get these crazy irrational numbers. So now I can go ahead and just plot all those points here. Try to do it to the best of my ability. Let's see. Notice how I left a lot of room on this side because all my x coordinates are positive. So we got 1 at 2.5, comma 1, 2, 3 right here. I have 1 at 3, comma 2 right there. I have 1 at 9/2, that's 4.5. 1, 2, 3, 4.5, comma 1. And I have 1 at 7, comma 0. 1, 2, 3, 4, 5, 6, 7, comma 0. And so our square root graph is going to look like that. Okay? Remember that the square root function has a clear starting point and then extends in one direction. All right? A couple other things we need to find about this function are the transformations, domain, and range. So the transformations refer to how did the function change from our regular old parent function. Our regular old square root parent function starts at 0, 0 and goes up like this. So how did this change? Well, its starting position changed. It moved to the right by 2.5 units or 5/2 units. It moved up 3 units. And it no longer has a stretch of 1. It has a stretch now of -1. You can word that as it is now reflected over the x-axis, which if you remember is kind of a fancy way to just say it's flipped upside down. Flipped upside down. Okay? So those would be your transformations. Your domain is the region that the function occupies on the graph. How far to the left does the function go? How far to the right does the function go? The furthest left that we go, it looks like is 2.5, including 2.5, or sorry, 5/2. I meant to write 2.5 as a fraction, cheapers. And the furthest right we go is we go on forever, so infinity. The range is the same kind of question, but now we're looking from bottom to top. What space does the function occupy? If you notice, the function is going to go down forever, so it'll be negative infinity. The function is not going to go up forever, though. It's only going to go up to 3, so it's negative infinity to 3. All right? And that would be definitely a fair question that you'd be expected to do on any sort of assessment. Any question about that? Let's transition now into a cube root function. So if I were to do a cube root function, it's a very similar structure to a square root function. I'll do one with a little GCF and factoring, just so you see that as well. Let's do 3/2 times the cube root of, let's do 8x plus 16, and then we'll do a -1 on the outside here. Okay? So you may look at a problem like that right away and be like, ugh, Mr. Giorgio, this is a disgusting looking problem. And I completely agree with you. This is a disgusting looking problem. But we can make this problem not so disgusting. And we could do that by taking out a little GCF in the middle. So I can simplify this problem. Before I dive in and try to make my table of values, we can make a little simplification by taking out that GCF of 8, which leaves me with x plus 2 under the radical. This -1 still chilling on the outside. The benefit of that is we now have the cube root of 8 times x plus 2, which is equivalent to the cube root of 8 times the cube root of x plus 2, -1. Because the cube root of 8 times the cube root of x plus 2 would be the cube root of 8 times x plus 2. Now, the cube root of 8, you might be like, oh, the cube root of 8 is just 2. So I'm left with 3/2 times 2 times the cube root of x plus 2, and then -1. And then you could see that 3/2 times 2, the 2's would cancel out, and you would just have 3 times the cube root of x plus 2 -1, which is a much more manageable and simple problem at this point. Does anyone have a question as to that simplification process and how that's done? We seem all right. So now I can go ahead and make my table of values. I will do that. I'm trying to think of where to put it. Let's put it down here. I think I can fit it down here. Okay. Remember, with a cube root function, instead of looking to those values of 0, 1, 4, and 9 as our goals, we're going to be looking to the perfect cubes now as our goals, because the perfect squares worked great when we dealt with square roots, but now we're not in the world of square roots now. We're in the realm of cube roots. So in order to do that, my goals here are going to be the cube root of 0 right in the middle, because the cube root has a center point. It extends in the positive direction. The cube root of 1 and the cube root of 8 are your two first perfect cubes in the positive direction. And it also extends in the negative direction, because you can take the cube root of -1 and the cube root of -8. Okay? So let's see what we can do from here. I always like to start in the middle, go positive, and then negative. You could certainly start at the -8 and just go straight down. It's entirely up to you. But I would look and I'd say, what value is going to allow me to take the cube root of 0 in the middle? That part I can get right off the top of my head. That's negative 2. Because negative 2 plus 2 would be 0. The cube root of 0 is 0. Times 3 is still 0. Minus 1 is negative 1. So your starting point would be, your center point rather, in a cube root would be negative 2, negative 1, right? That's your center. Looking to see what value is going to give us positive 1 now, it looks like that would be negative 1, right? Because negative 1 plus 2 is positive 1. The cube root of 1 is 1. Times 3 is 3. Minus 1 is 2. Now looking to get 8, I believe the value we'll need is 6, because 6 plus 2 is 8. The cube root of 8 is 2. Again, that's the benefit of picking the perfect cubes. We don't end up with ugly decimals here. We get 2 times 3 is 6, minus 1 is 5. Just going back in the negative direction now, to get negative 1, I believe we need negative 3, because negative 3 plus 2 would be negative 1. The cube root of negative 1 is negative 1, times 3 is negative 3, minus 1 is negative 4. And last but most certainly not least, we're looking to get negative 8 here. What value for x is going to give us negative 8? I believe that's negative 10, because negative 10 plus 2 would be negative 8. The cube root of negative 8 is negative 2, times 3 is negative 6, minus 1 is negative 7. Okay. Does everybody understand how I was able to complete that? Okay. Now that I have that chart, I can go ahead and sketch my values here. Looks like we need a lot of room on the x-axis and on the y-axis. So I think we should have enough here. Yeah, we should have plenty of room. Okay, so let's see where my chart lies. We have our center point at negative 2, negative 1. That's going to be right there. We have going in the positive direction, we're at negative 1, comma 2. We're at 6, comma 5. 1, 2, 3, 4, 5, 6, comma 1, 2, 3, 4, 5 right there. In the negative direction, we have negative 3, comma negative 4. And lastly, we have negative 10, comma negative 7. Negative 1, 2, 3, 4, 5, 6, 7, 8, 9. Oop, we need one more. That was really ugly. 10, comma negative 7. 1, 2, 3, 4, 5, 6, 7. Right there. Okay. If you notice, your cube root function does make that S shape, which you expect it to make. So we can just go ahead and connect these all to the best of our ability here. And it looks kind of like that. There we go. That wasn't so bad. A little iffy around there, but not bad. Okay. Any questions about that, how we constructed that graph? Just like before, we're looking to find the transformations, the domain, and the range. So let's start with your transformations. Transformations is referring to the center point, because normally with just regular old cube root of x, your center point would be at the origin, 0, 0. It's not at the origin anymore. It is now moved left 2 units. It has also moved down 1 unit. And it has a stretch now of 3. I want to echo, I believe it was Luke who asked it a couple classes ago. He said, when you're going to write the transformations, can you instead say it has a horizontal shift of negative 2, a vertical shift of negative 1, and a stretch of 3? Absolutely. However you can communicate that movement to me is perfectly acceptable. All right. And domain and range is actually pretty easy, because with any cube root function, your domain and range is all real numbers, because it's always going to extend forever to the left and right, and forever up and down with any cube root function. Not square root, but any cube root. Okay. Any other graphing related questions before I go back and show you a couple of solving equations examples? Feeling fine? Doing great out there, Algebra 2? It's all quiet on the Western Front out there, but hopefully we're doing fine. All right, so let's transition to solving. If you do have a question though, like don't feel free to say anything. No, if you have a question, feel free to interrupt and just chime in, or just type it in the chat. Okay, so let's go into a couple of solving equations examples. I'll start with this one. It's as good as any. Let's do negative 5 is equal to the square root of x plus 15, and then minus x on the outside. So if you're dealing with a problem like this, first thing you'd probably want to do in order to solve for x is to isolate the radical. We do that by adding x to both sides. That gives me x minus 5 is equal to the square root of x plus 15. Okay, does everybody see why it's beneficial to do that? If we don't do that and you just square both sides right away, you have to do some distribution with this. And although that is certainly something you can handle because we've done distribution like that, I'd rather avoid it if possible. And so let's isolate that radical so we can avoid. Now I can square both sides, and we will have to do distribution on the left, but that left distribution is much simpler. We have to do x minus 5 times itself because that's what it means to square something. And that's equal to x plus 15. Excuse me, a little distributive, oh god, I'm dying. Little distributive property going on. On that side, we got x squared minus 10x plus 25 is equal to x plus 15. Okay. We just have to now set up to factor, because as soon as you see that x squared, you should be like, ooh, factoring. But remember, to factor, we have to set equal to 0, so I'm going to do exactly that. That gives us now x squared minus 11, excuse me, x plus 10 is equal to 0. Okay. That now breaks down into two binomials. Nice classic algebra 2 factoring. We need x and x to multiply to x squared. I need both negatives to multiply to a positive number. And it looks like in order to get negative 11, I'm going to need the factors of 10 and 1. That gives us two potential solutions, one of x equals 10 and one of x equals 1, positive 1. Okay. We can now go ahead and check for extraneous solutions by saying, well, let's make sure. When x is equal to 10, is it true that negative 5 is equal to the square root of 10 plus 15 and then minus 10? Is that true? I believe it is. We get negative 5 is equal to the square root of 25, which is 5, minus 10. And 5 minus 10, by my count, is equal to negative 5, so I'm happy with that. Happy with that. We got one good solution. Let's check. When x is equal to 1, is it true that negative 5 is equal to the square root of 1 plus 15 minus 1? This one I'm a little less convinced. We got the square root of 16 minus 1. 4 minus 1 is definitely not equal to negative 5. I don't like it. Don't like it. So this one is extraneous. But we did at least have one real solution here, and that one real solution was x equals 10. Okay. Any questions, comments, concerns as to how that problem was done at all? None? No questions? It was crystal clear? 100%? I mean, that's great if it was. Everybody's feeling good. Everybody's confident, I guess. Everybody's comfortable, confident, cool, calm, and collected. All right, fantastic. So let's do one double distribution problem in our last 5 minutes here, and that should be good. Okay. We've done a lot of these now in a couple class periods, so I'll go through this one a little faster than you might be used to. You might be like, ugh, double distribution problem. That's going to take like 10 minutes, but I'll get through it in 5. Ready? We got square root of 3x minus 3 equals square root of 5x minus 4 and then minus 1. Notice again, it does require that double distribution because it's impossible to isolate both radicals simultaneously. In order to do that, watch. Square both sides. Square and square root cancel out there. I get 3x minus 3. Over here, little first, outer, inner, last is going to be required because I need to take this square root of 5x minus 4 and then minus 1 and multiply that by itself. Just like that. Okay. Here I get 3x minus 3 on the left. Here I get the square root of 5x minus 4 times the square root of 5x minus 4 is just 5x minus 4. Here, the square root of 5x minus 4 times negative 1 is exactly that. Negative 1 square root of 5x minus 4. We get another one on the inside here, another negative 1 square root of 5x minus 4. And then negative 1 times negative 1 is positive 1. Okay. Combine some like terms on that right side to clean it up. I get, let's see, this 5x can't really combine with anything. This negative 4 and this positive 1 can, though. That becomes negative 3. And here I have negative 1 of these and another negative 1 of these. That altogether makes negative 2 square roots of 5x minus 4, just like that. Okay. Again, it's a very tempting and very common mistake that a lot of students like to take a look at this and be like, ooh, this is negative 5. But remember, please, please, please do not do that. This is attached to this term here, so we cannot separate it. Okay. Now, I can, though, isolate the radical and prepare to square both sides again. I can get ready to do that by subtracting 5x from both sides, adding 3 to both sides. Ooh, kind of interesting thing here. Negative 3 plus 3 is going to go away. That's convenient. Here I get negative 2x is equal to negative 2 times the square root of 5x minus 4. This problem is full of conveniences because if you look again, it's making my day right now. I didn't do this problem beforehand. I just pulled it up and I was like, wow, this problem's making my day. Divide everything by negative 2. That's going to cancel out on both sides, right? Remember, at this point, if you can divide by the coefficient, it's always beneficial to do so because it's just going to reduce the numbers that you're working with. Here I get now x is equal to square root of 5x minus 4. We can square both sides. Nice and easy now, wow. Here I get x squared on the left. Here I get 5x minus 4 on the right. Let's just set equal to 0 by moving everything over to join up with x squared. That gives me now x squared minus 5x plus 4 is equal to 0. That factors down to x minus 4 and x minus 1. So that gives us two potential solutions, one of x equals 4 and one of x equals 1. Does anybody have a question as to how we solved that problem? That was nice. I'm actually glad that that canceled out there. That made it a lot faster. Now that we have those, we can, of course, check for extraneous solutions. So we're going all the way back up to the top to plug in right up there. I'm going to see, is it true? Just trying to center my paper again. Let's check. When x is equal to 4, is it true that the square root of 3 times 4 minus 3 is equal to the square root of 5 times 4 minus 4 and then minus 1? Is that true? 3 times 4 is 12 minus 3 is 9. So here we get the square root of 9, which is 3. Is that equal to the square root of 16 minus 1? I believe it is. 3 is equal to 3, so I'm happy with that. And then let's just check the other one really fast. If x is equal to 1, is it true that the square root of 3 times 1 minus 3, so 0, is equal to the square root of 5 times 1 minus 4 and then minus 1? Okay, get on there. All right, good. Yeah, I think it definitely is. If you take a look there, I get 3, this is the square root of 0. I get the square root of 1 minus 1, which is also 0. Okay, so this problem does have two solutions, one of x equals 4 and one of x equals 1. Any questions, comments, concerns at all, even in the slightest, about these problems? No questions? We're feeling fine? We're doing fantastic? All right. Well, that just about brings us to the end of class. One thing I will say is if, for whatever reason, you did not submit the progress assessment yet, it was due at the start of class, but please, please, please get it to me at least by the end of the day because I am going to grade them tomorrow and get feedback to you tomorrow. Pretty much what I'm going to do, what I think I'm going to do is I'm going to post an answer key to the progress assessment for you on Classroom. And I'm going to send out an email that says if you want specific feedback on the grade that you received, you can feel free to ask, and I'll be happy to provide that to you. But I think by looking at the work you submitted and comparing it to the answer key, you can see where things went wrong. So I think that's probably a good way to get that feedback back to you. And you'll see your grade in Aspen to be like, oh, this is what I messed up, and this is how much credit I may have taken off or may have given you. So if you do have any specific feedback questions, though, if you're like, why did I get this grade on this particular thing, I'll be more than happy to address that, all right? But I will post the answer key to the progress assessment tomorrow, so you can go ahead and take a look at that if you so desire. We don't have classes tomorrow, though, so you got all weekend to check that out. Next time we see each other is Tuesday, the 14th. That is our summative day. So I will see you then. Thank you for your attention and focus today. Again, remember to sign in on attendance if you haven't done so already, but have a fantastic rest of your Wednesday.